In Chapter 7, we're going to learn about some different types of functions, some new functions that we've probably never seen before, like the hyperbolic functions, and some old functions that we definitely have seen before, logarithmic and exponential. So in section 7.1, we're just going to revisit logarithmic and exponential functions. You might have already seen some of this, especially the basics of them, but you may not have seen the derivatives and integrals of them. And we're going to talk about all of that. All right, so let's begin with the natural logarithm. Now, we can define the natural logarithm several ways, but there's a really elegant way to define the natural logarithm, which is that the natural logarithm is, by definition, the integral of 1 over t dt from 1 to x. So if we're going from 1 over t in the positive direction, or 1 to t, so 1 to x right here, going in the positive direction, it would make it positive, right? So the natural log would be greater than 0 because you're heading from 1 to the right. If you go left, we learned in Calc 1 that if you take an integral and you start at 1 and you work your way this way, then it will be negative, which is why it is less than 0. Because logarithms can be 0 and logarithms can be negative. It's just you cannot take the logarithm of 0 or a negative number. So logarithms, in other words, can have negative numbers as their output. They just cannot have negative numbers as their input. All right, so let's remind ourselves of some properties of logarithms. So what I just said right here, logarithms have a domain of 0 to infinity, right? But a range of negative infinity to infinity. So a logarithm can be negative, but you cannot take the logarithm of a negative. So I guess I'll just make a little note. Natural log of 0 and the natural log of a negative number are both impossible. They cannot be done. Next, we should have learned in algebra class somewhere along the line these three properties. They are the product property, the quotient property, and the power property of logarithms. So they're pretty basic. I believe they're in your sheet packet of notes somewhere as a quick reference. But they're also just something we should all know, right? The logarithm of x times y is the logarithm of x plus the log of y. Log of x divided by y is the log of x minus the log of y. There's actually a change of base, but we wouldn't care about that for the natural logarithm. And then the power property, the log of a to a power is that power times the log of a. So these are written out in general form with any logarithm, but of course if they're true of any logarithm, then they're also true of the natural logarithm, which is the log that we actually use the most by far, especially in science class. Next, the derivative of the natural log of x is 1 over x. We all probably learned that in Calc 1. It is on the derivative sheet, but not every Calc 1 teacher makes you memorize it. So it's right here. The derivative of natural log is 1 over u times u prime, of course, if you're using chain rule. So if it's not just the natural log of x. So this is number 11 on your gold sheet or whatever color sheet. I'll just say number 11 on derivative quick sheet. Actually, both of these are number 11. This is just a simpler version of this, right? And then the integral of 1 over x, well, by definition, is natural log of x. That's how you can define the natural log of x. Now, there's one important point to notice that a lot of students forget, which is that it does have to have an absolute value. So the absolute value has to be there, and students sometimes drop it because usually in Calc 1 we're not dealing with tricky problems, but technically there should be an absolute value in there, right? So that's number 5 on the integral quick reference sheet. Oop, I forgot my C there, quick sheet. There we go. All right, so let's use them. I mean, if we know their derivatives and integrals, that means we should be able, hypothetically, to use them to find some derivatives and integrals. Obviously, the derivative is a lot easier. That's why I made it go quickly. There's not a lot of space for the derivative problem. All right, so we have one function nested inside another. As a matter of fact, we have more than that. Let me rewrite this. This is equal to taking the derivative with respect to x of the natural log of the cosine of x cubed. We don't write it that way, but that's what it is. We're too lazy to actually put a bracket and put a cube out in front, so we put it over there after the cosine. Okay, so when I want the derivative, I want to apply chain rules over and over and over. So I start with the outermost function, and I take the derivative of that, which in this case would be the natural log. So that's the outermost piece. So the derivative of natural log is 1 over, and then leave everything else alone. Then I multiply it by the derivative of the next piece. Well, the next piece is the cube. It's not the cosine. Cosine's nested inside an exponential, and we all learn, please excuse my dear Aunt Sally. So the cube part matters next. So we bring the 3 down, and then leave the cosine of x alone and square it. And then we multiply it by the derivative of the inside, and the derivative of cosine is negative sine of x. So it's a double chain rule. All right, well then we can kind of clean this up. So this is negative 3 sine of x cosine squared x over cosine cubed x, which would be negative 3 sine of x over cosine of x. But the sine of x over the cosine of x is the tangent of x. Amazing, isn't it? All that complication, and that is the derivative. It's a simpler problem than what we started with. All right, so now let's try the next one. So where you're going to run into trouble right now is that you have to figure out what u substitution you're going to use, right? So if you tried, I mean, what a lot of students would do is try u equals x squared. And that's fine and good. If you try u equals x squared, du is 2x dx. But the problem is you have an x in the denominator, not an x in the numerator, which is what this is. Boo. So that's not going to work. All right, so then you think, well, okay, it's 1 over all of this. So let me try u equals x natural log of x squared. All right, well, then the derivative would require the product rule. It'd be 1 times the natural log of x squared plus x times 1 over x squared times 2x, which would be the natural log of x squared plus 2. That's not in the problem anywhere. Oh, all times dx, right? Boo. That didn't work either. All right, well, what is going to work? Well, I will tell you. It's the natural log of x squared. It'll work. Because if it's the natural log of x squared, then du is 1 over x squared times the derivative of the inside, which is 2x. Which means dx. Which means du is 2 over x dx. Looking at the problem, I want the over x and the dx part. I don't really want the 2. So 1/2 du would be equal to 1 over x dx. This will work. This is the one. All right, so let's rewrite the problem. So it was the integral of 1 over x, natural log of x squared. 1 over x dx is the same thing as 1/2 and then du. And then it's 1 over u. Right? Because I have a 1 over, and then that's a u right there. And then the x and the dx. So here we go. This is u. And the x and the dx are taken care of by the 1/2 du. Okay, so this is equal to 1/2 the integral of u to the negative 1. Oop, that looks like a weird symbol there. Negative 1 du. Okay, but the integral of 1 over u to the negative 1, you might think, oh, I'll just add 1 to the power. But if you add 1 to the power, you get 0. And there's no way the derivative of 0 is 1 over u. That doesn't work. So what this is 1/2 natural log of the absolute value of u plus c. And that would be 1/2 natural log of the natural log of x squared plus c. And yes, you do have to use the absolute values because the natural log of x squared could be negative. And so you have to have absolute values in there because you cannot take the log of a negative number.